And that's okay. Now that we know what salinity and pH are, what are their effects? Why are we concerned about them? What are their effects on plant nutrient availability and uptake? So let's first focus in on salinity. You remember this graphic I used earlier to talk about dissolved ions in solution. Most of the dissolved ions, as it turns out from our minerals, are also nutrient elements. The plant needs calcium, and the plant needs potassium and magnesium and sodium and sulfate and so forth, sulfur. And so as these ions are dissolved from these minerals, they become available also as nutrients. So in a normal condition, like we would see here graphically expressed, we have a good amount of water. We have lots of dissolved nutrient as well in that water, and the plant is happy. It can have delivered to its root surface rather readily both water and nutrient, and then they're taken up simultaneously in the transpiration stream, and the plant can use it. But when we start getting excessive amounts of solute dissolved in the solution, then it becomes harder, not only for the water to move across the root membrane, but for individual elements to come in contact with the root surface as it deals with all of just the gridlock that can happen with the movement and fusion of various ions to the root surfaces. I've demonstrated that here with maybe an extreme example where we have not only the need for calcium in the plant, but also potassium and sulfur. But in a situation where we have lots and lots of calcium salts dissolved in the situation or in the solution, it's going to be much harder for the plant to encounter that potassium ion that it needs as well, as it's competing for positioning at the root surface for uptake. And so we call that uptake competition. So even though those elements that are dissolved in the solution might be necessary nutrient elements, we can get this competition where it's difficult sometimes for some of the nutrients in smaller quantities in that solution to find themselves at the root surface available for uptake. We can also get a situation which we call nutrient precipitation. And precipitation is the removal of a solubilized ion out of solution and back into a solid form of some sort. And so in our soils where we have very high carbonate content, we have a lot of lime in our soils, and we have a lot of carbonate and bicarbonate dissolved in our water, both our well waters, our surface waters, our tap waters, and other things. We can get precipitation or the removal of soluble calcium out of the system into solid lime. Now, every single one of you have dealt with this in one way or another in your home. You have all faucets in your bathrooms, I'm sure, that over time begin to accumulate hard water deposits if you don't have a water softener. Our water has so much dissolved carbonate and bicarbonate in it, it begins to precipitate calcium in the water. Our hard water has a lot of dissolved calcium and magnesium salts. And so at the outflow part of our faucet, we get this reaction happening, and we get the precipitation of limescale that begins to form on the faucet. And this happens in the soil as well. If we have lots of dissolved carbonate and bicarbonate in solution, it can attach to the calcium and precipitate solid lime. And so it takes available calcium out of competition, or out of opportunity anyway, for the plant to take it up, maybe sufficiently. And that would be a nutrient precipitation reaction. We have a number of these, and I'll cover a few of them at the end that we typically deal with. We not only have precipitation with additional things like carbonate and bicarbonate, like in a high lime condition, but as the soil solution concentrates, as water evaporates away and leaves the salts behind in solution, or as the plant takes water out of the system and leaves the salts behind, the salts will concentrate to levels where they can go from being dissolved in the solution back into their original mineral salt forms. We saw this graph earlier when we were talking about just the dissolving of those into solution, but it's a two-way street. If we get increasing concentration on the dissolved side, it can push back to the solid side of those reactions. And so that's, again, a precipitation reaction that can take important nutrients that are dissolved in soil solutions out of the solution and into solid forms that are no longer available for uptake by the plant. And so we see oftentimes in situations where we wouldn't expect it sometimes that we have nutrient deficiencies showing up because of some of these reactions I've talked about. Here's a really good example. This is strawberry showing a calcium deficiency in a very high calcium soil or calcium condition. And the reason is that we had enough dissolved carbonate in the system that calcium began to precipitate out of solution, and you had a harder and harder time for the plant to take up the calcium that it needed as we had rapid growth in these strawberries. So we see this telltale sign of calcium deficiency, the cupping and folding of the strawberry leaf. And this is a nutrient precipitation effect. We didn't expect seeing it because we knew we had play of calcium in the fertilizer that was being applied and so forth. But the precipitation that was taking place was taking it out of solution. We saw this graph earlier when I was talking about the effect of pH on the solubility of iron. As we get increasing pH, we can get precipitation reactions from iron going from being soluble at acid pHs to very insoluble at basic or alkaline pHs. And so this is why pH becomes an influencer on nutrient availability as well. If you take a look at phosphorus, phosphorus is one that we deal with all the time in terms of availability in our higher pH soils. And this is very similar to the graph here, except it's a little bit more complex because there's more solid forms showing up. But the same principle applies. These lines show the decrease in available phosphorus as we get increasing pH, because it begins to precipitate into solid forms. And in our case, calcium phosphate is the form that begins to precipitate in our alkaline soils with high calcium in them. And it takes phosphorus, important and a very important nutrient element, out of solution and unavailable to the plant. And so as we get increasing pH, we see differences across the entire scale in terms of the availability of the important nutrients for plants. Nitrogen, broadly available across a very wide range of pHs. The same thing for potassium and sulfur, but then we start looking at some of these that get involved in these precipitation reactions and the re-solidifying of some of these minerals into very insoluble forms. Iron is probably one of our most important one that we end up dealing with, and zinc in our high pH soils, as they precipitate into solid forms at our higher pHs. Most of us are going to find that our soils are somewhere between 7.5 and 8.5 in our arid, semi-arid areas in the Western US, because we are in situations that have a lot of lime content, a lot of basic cation salt content as well. And so we're buffered up here at these higher pHs, and it doesn't change much. And so we're always going to be dealing with difficulties in making iron available to our plants, and difficulties in making zinc available to our plants, and difficulty in making phosphorus available to our plants because of these. And so when we know the pH and we can measure the pH accurately, we can get a really good idea of how what kinds of nutrient challenges, nutrient supply challenges we're going to encounter in that particular soil. So mineral precipitation is also driven by pH changes. And I put a couple of common precipitation situations that we have, reactions: calcium with phosphorus to form calcium phosphate, zinc reacting with phosphorus to make zinc phosphate, iron and sulfate reacting at higher pHs to form iron sulfate. This is pyrite and zinc phosphate, apatite minerals and things like that that begin to then form, that are very insoluble. And then we get the loss of not only the zinc or the iron or the calcium, but also the phosphorus and sulfur in those particular reactions. So I get a lot of questions. If that's the case, if pH drives so much the availability, particularly of these really challenging elements like iron and zinc, why don't we just change the pH of the soil? Why don't we just adjust it to more acidic conditions? And I'll give you an idea of why that's a very difficult problem of scale in our alkaline soils. We have a lot of buffering compounds in our soils, particularly in our high calcareous soils or high lime conditions. We talked about the problem of scale. We see it happening. We see that lime scale forming on our faucets and inside our water heaters and other things that we get concerned about. Well, that calcium carbonate, that lime material, buffers pH change. So let's take a look at that here as it kind of just qualitatively anyway, as we look at the change in soil pH with increasing amounts of added acid to the system. So down here on the bottom axis, you have increasing acid load. And on the y-axis, you have the soil pH. Where we have lots of calcium carbonate or lime in our system, as that lime begins to dissolve, it consumes the acid that's being applied and neutralizes that acid to the extent that nothing changes in terms of pH until all of the calcium carbonate has been dissolved. At that point, we can then begin to lower pH. Well, we're like, okay, great. Well, why don't we just do that? Why don't we add enough acid to be able to solubilize that calcium carbonate in the soil and begin to lower our pH so we get better nutrient availability for iron and zinc and phosphorus and other things? Well, let's take a look. This reaction, this neutralization reaction that happens when calcium carbonate dissolves, is very instantaneous. It happens very, very quickly. And we get the production of carbon dioxide gas and water. So we get no net change in hydrogen ion in the system. It's consumed. It leaves additional calcium back in the system that can continue to react and so forth. We said that all lime would have to be dissolved before we can start to drop the pH. In our Utah soils, and most of the western United States for that matter, except for pockets in the Pacific Northwest, up in the Idaho Panhandle and other places, some places up in northern Montana and other places in the west, most of our soils are very high in calcium carbonate content. In fact, 15 to 40% by weight in terms of lime content. Down in the southern Saratoga Springs, up into Eagle Mountain area, things like that, I've seen soils as high as 50+% calcium carbonate by weight. If you take a soil at 15%, and you take an acre of that soil and just look at the top foot of that acre, that's 300 tons at 15% calcium carbonate of lime content in that soil. 300 tons of lime would have to be completely dissolved before you can start to lower the pH of that particular soil at 15% calcium carbonate by weight. So we're talking about a problem of scale that's unmanageable. It's a non-starter for most of us in Utah and in the western United States to really alter the pH of the system because of this. In fact, if we get up in higher contents, which is not uncommon, soils right here around Utah State University are anywhere from 20 to 30% calcium carbonate. We're starting to get up into the 500 ton per acre level of carbonate content. And so this reaction takes place almost immediately. And so we don't really get a net change in pH in those systems where we have excess lime in the system. I'm going to play this little 1-minute video, and it doesn't really matter if you can see or hear it. I'll run it anyway. What the person's going to do in a laboratory setting is put a little bit of calcium carbonate into a test tube and add a very dilute acid, hydrochloric acid, and we're going to watch how quickly the reaction takes place and begins to produce carbon dioxide and the other byproduct of water. So let's just watch this real quickly here. Well, it's not activating. Here we go. Are you seeing it or not? Neil, let me know.
I'm not seeing it.
Okay. I'd have to change the share screen. So I think what we'll do is just throw that out. Well, what's that, Neil?
I was wondering if you could just minimize the screen a little bit and then see your thing on the bottom and get it on the same screen, but maybe it works and maybe it doesn't. It might not.
Well, it opened up my browser and activated YouTube, and I think it's going to be too complex to share it. So, well, let me try this.
Just drag it to where the screen you're looking at.
Are you seeing that now?
Not yet.
All right.
Try copying and pasting the link into the chat. I can't because I can't do it, but just from your regular PowerPoint, just paste that link into the chat and I'll see if I can bring it up.
Well, it's not letting me even do that. So I'll make that available. You'll be able to copy and paste that when you see it. It's a 1-minute long video, and it just shows immediate effervescence of the calcium carbonate being produced from a little bit of acid addition to the test tube. It's a very instantaneous reaction, takes place immediately and consumes any acid that's being applied rather readily and buffers the pH change so that we get no net decrease in pH with the addition of acid load. It would take pound for pound pure sulfuric acid to affect that dissolution of calcium carbonate in our soils. And number one, we don't have enough money to buy that much acid to make that change. And number two, a soil that's 40–50% calcium carbonate by weight, you've decreased your soil material by almost half. Half of it's completely gone back to the atmosphere as carbon dioxide and drained out as water. So it's kind of a non-starter situation for changing the pH. So since we can't do that, how do we manage nutrients in a high pH and high salinity condition? And so this is really what I wanted to end off with here. In terms of salinity, remember that I wanted you to think about the fact that each of those little dissolved ions in solution is an atom of that particular element, nutrient element. So it's an atom of sodium or an atom of chlorine or an atom of calcium, etc. And I can't create nor destroy matter. Those are the basic building blocks of matter. I can only remove them from the system some way. And so we do that by washing them from the system. Most of these are mobile with the water in the soil. And so if I have good open drainage conditions in the soil, if I've helped keep soil structure up so that I have good pore structure and drainage from the system, then I can put water of lower salt content onto the soil and wash the soil salts, the dissolved salts, out of the material and down to deeper depths where they're not going to cause injury to the plant. the rule of thumb, and I didn't put this in the slide, but it will be in the recording. The rule of thumb is that if I can put 6 inches of water per foot of soil over and above the water holding capacity of the soil, I can affect about a 50% drop in soluble salt content out of that foot of soil. And if I can clean up a foot of soil like that with a leaching event like that, I can typically get the salinity, the soil salinity down to levels that are not injurious to things like my vegetable garden or my ornamental flower bed or my fruit tree, for instance. That's not something you have to do every single year. That's a reclamation kind of product or project. If I have too much salt and I'm seeing salt injury, I can put a leaching event on and I can reclaim that, push it down to deeper depths where it's not going to cause an issue. And I physically wash the salt out of the soil matrix. Do not let somebody talk you into purchasing an amendment that will neutralize salt in soils. Typically what these are long chain organic molecules that have a lot of charge on their surface. And so they attract these ions to the surface and they absorb to the surface or they stick to it. And it temporarily takes them out of solution, which is fine, but it's an organic molecule. So over time, the microbes in the soil are going to break that molecule down and re-release those salt ions back into solution. And so you're never going to really get rid of them in that situation. The best way is to physically wash them away. And so if people have a concern with that, they got too much salt and they know what the salt level is, we can give them some prescriptive procedures to bring that down to a level that will not be injurious to the plant. We also caution people against the over application of fertilizers. Fertilizers are nothing more, at least the mineral fertilizers, they're the soluble salts of the various nutrient elements that we're interested in obtaining. And so a soluble fertilizer for iron, for instance, is iron sulfate. It's the mineral salt of iron, and it will dissolve in the soil solution and provide that available nutrient for a time. But we know that at high pH, that iron's going to want to fall back into a solid form. But those are the soluble salts of the mineral elements, those nutrient or mineral fertilizers. If we apply them over and above the need of the plant for that particular element, all we're adding is excess salt. And you have all seen this happen as you've put your fertilizer out on your lawn in the spring. If your spreader got too much overlap in one little place, or if you were hand broadcasting it and you dropped a little bit of fertilizer in a pile in one little location, and you tried to kind of spread it out a little bit right where it fell, you'll notice that you get a little burn spot there. It starts to yellow, or maybe if it's extreme, it'll dry out completely. And that's because of the salt index of the mineral fertilizer that landed in that location. It basically locks up the water and won't let the plants in that location take water up, and they begin to dry out and die. And so we see that happening all the time with mineral fertilizers. So don't over apply mineral fertilizers, or you're just adding additional salt to the system. You see the same thing with pet urine stains and things like that in your yard. The dissolved salts in the urine cause the same kind of effect. You see the yellowing, and if it gets too bad, you'll see that necrosis happening of the material too. And that's a salt issue. So you can leach the salts out, make sure you get out there and water them down good where you see your dogs and other pets maybe doing their thing in your yard. So we want to manage our soil moisture at optimum levels. Remember, as we got higher and higher concentration, less and less water in the system, we could get nutrient precipitation reactions happening. And so it's good if we don't go into extreme drying cycles and things in our soils when we're trying to make sure that the nutrients are are properly made available to plants at critical times. So particularly at flowering stages of vegetables, the different fruiting stages as the fruit is forming and trying to fill and things like that. These are times we want those nutrients flowing in and we want the water flowing in. And so we want to keep the soils at optimum water levels for that to happen. A lot of people will note that if you're using drip irrigation, you can get by with using a water that it's a little higher in salt content, because you're constantly keeping the soil at an optimum water content so that we don't get these competitive reactions, we don't get some of the dissolution reactions, and the water is more available for uptake by the plant. Where we have high pH conditions that cause problems with iron and zinc availability, we would recommend the application of chelated forms of iron and zinc. Chelated forms are carriers where the iron or zinc are fixed to a molecule that's a carrier molecule that keeps it sequestered away from some of these reactions in soils and allows it to be more time released in the system. If you're going to apply a chelate of iron, for instance, to a soil, make sure you're using the EDDHA form. And somebody can help me by putting that in the Q&A response. The EDDHA form of the chelate. You'll often see that expressed as a number too. It's expressed as number 138 on many of the chelates. So if you see a chelate that's sequestrine 138 or something like that, it's the EDDHA form. And that particular chelate is stable at high pH conditions in our soils. Some of the other chelates that are also readily available out there, DTPA or EDTA, these are very unstable at high pH conditions. They'll break down so quickly that they won't give you kind of the net prolonged availability of the iron in our soil systems. But these can also be applied as a foliar application. We do this all the time in our raspberries in my garden. Raspberries are fairly inefficient, and many of the varieties at taking iron up out of the soil. And so I will take early in the spring as those leaves are beginning to start to expand. I know I'm going to have iron deficiency issues from my soil. I'll mix up iron chelate solution and I'll spray it directly on the plants. And I'll do that several times over the course of the spring and early summer, just to make sure that there's plenty of iron in those leaves to produce the chlorophyll that's needed to get optimal growth and production out of them. So we can use foliar application of these. We can do it in soil applications as well. If you have a water that's really high in bicarbonate or carbonate, you can actually do some acid treatment. If you're in a production setting, this will happen. A homeowner setting, typically we don't want to really handle the acid. It's dangerous to do so. But you'll find in a production setting where you can inject acid into the well water, or use a sulfur burner to inject acid into the well water. What will happen is you'll get that reaction where the acid will be consumed by the carbonate and create carbon dioxide gas and additional water. And so the carbon dioxide gas will go off, and the acid will be consumed, and you'll get a net drop in terms of or increase, less acidity, less carbonate in the system that can cause precipitation reactions and so forth. So,
Grant, there's a couple questions.
4 or 5 minutes here, we can answer some additional questions.
So, can you read the questions, or do you want me to read them to you?
I've got them right here. So
Okay.
the first one that I can see anyway is with a small home garden, is it economically possible? Let's see. Do you recommend avoiding the whole salinity problem and just buying raised bed soil? yes and no. If it's not terribly high in terms of salinity, and you can do some simple leaching reclamation, if your soil has good structure or it's a little coarser texture and we can get a good leach, then we'd want to probably go that way, and then amend our soils with good organic matter to keep them open, and maybe adding a little bit of extra irrigation water to continually move the salts down through the system. If you're really, really, really high and you have a difficult soil, a high clay content soil, not really good structure, difficulty in drainage, maybe a high water table that doesn't allow for drainage, then going to a raised bed system is often quite helpful in overcoming a salinity issue. I would tell you that regardless of how good our water qualities are, both raw water, like secondary water for irrigation, or tap water, there is dissolved mineral in those soils. There's salts in those waters, and they can build up in grow boxes as well. And so you want to be able to make sure that you have an opportunity for flushing those on occasion if you get salt content buildup. We see that in potted plants in our homes all the time. If we have a herb garden, for instance, that we like, the basil and the coriander and other things right there available to us, over time, that calcium carbonate and the other salts that are dissolved in tap waters, for instance, in our homes, can build up in those pots and reduce the growth of the plant. And so we'd recommend repotting those or leaching them well and things like that on occasion to help reduce the salinity injury. Next one says, in a natural system, do microorganisms in the rhizosphere help increase the solubility of nutrients? And yes, that's true. The difficulty there is that it's independent of anything that we can do to try to encourage that. Those relationships happen fairly naturally. People will try to inoculate with additional mycorrhizae or other things to improve those conditions. And those are typically materials that aren't specific to the plant that we're trying to develop that relationship with. And so a lot of times we get into wasted expense in trying to encourage a mycorrhizal condition. There are rhizosphere reactions and mycorrhizae reactions that can help solubilize nutrient elements. And that's why some plants are more efficient at taking up iron, particularly iron and other nutrients. And so if you find a variety that has a good symbiotic relationship with mycorrhizae in a given area, they typically are more efficient at taking it up. So typically we don't recommend a lot of expense involved in trying to establish a mycorrhizal relationship, because it typically is a waste of money. But where we do have good relationships with some of the varieties that have been tested, shown to be more efficient, they will create those and help provide the nutrient. Great, thank you, Cody, for putting EDDHA up there, or again, 138 is the numerical value for that particular chelate. Somebody had a question here about Revive on dog urine. Revive is kind of a mixture of nutrient and organic materials and other things, soluble organic materials. And so what that product will typically do is help encourage good soil structure, good nutrient availability, help counterbalance maybe some of the salt influence. It doesn't neutralize the salt in any way. You still have to get water through that to wash the salt out, but it helps keep the soil open, provides additional organic matter to keep the structure in place, and helps bump up the nutrient content just a little bit to help with some of the precipitation reactions that can happen. So some of these amendments can help in the process, but the baseline process is keeping the soil open, allowing it to drain properly, and pushing water through it in order to get the salts out of that profile. But where those amendments can help accomplish that, then great, let's use them as we can. Person says they have a well water, 18 foot down, has a pH of 7.9 and a conductivity of 3.6. The pH of that water isn't terrible. That's basically in equilibrium with soluble calcium carbonate, typically what our soils would be around here. The salt content is concerning. Like I said, we put an irrigation water on, and the salts are typically going to concentrate in the soil solution anywhere from 2 to 3, even 4 times higher than the water content. And so you're 3.6 there in your well, you're going to be talking about eventual soil salinities in the neighborhood of 7 to 9, which is well above the death threshold for many of the things like vegetables and fruit trees and lawn turf species and other things. So in order to remediate that, you'd look at having to do something like ion exchange to remove the ions out of the water, or a reverse osmosis that basically strips the salt ions out of the water before you can really use that effectively for irrigation purposes. Somebody says skip the sulfur compounds. A lot of people will say gypsum is a good soil amendment. And it really is in situations where we don't have enough calcium. Calcium is a flocculating element. It's a divalent cation, so it can draw clay particles together and help keep them flocculated, and helps keep structure in place and things like that. But typically we have lots and lots and lots of calcium in our soils, and we don't need additional calcium. So adding gypsum, a sulfur product, basically to a soil that's already high in calcium is just adding additional salt. If we have a sodium imbalance, if we have way more sodium salt than calcium salt, then we can have a problem with clay dispersion. And in that case, then yes, adding a calcium sulfate like gypsum will help flocculate those clays and help improve soil structure. So it's very dependent on the kind of salt that's in the system. Most of our soils, we have plenty of calcium. We don't need the sulfur, the sulfate material. But if you have a sodium imbalance, then that's the one instance where it's a good idea. Now, you can get a good maybe ballpark idea if you've got a sodium issue. If your pH gets up above about 8.3, 8.4. If we start getting into those pH levels, then we typically look for a sodium problem where gypsum could benefit us. Can you speak briefly about the development of caliche?
Grant, just looking at the time.
Oh, yes, I did.
We should jump into Melanie's